Okay, this lecture we're going to get into some details, important details, introduction of important details of flowing fluids, liquids, or gases. So, one of the most important distinctions you can have for flowing liquid, and it'll be provided in a demonstration with this after this lecture, is going to be laminar versus turbulent flows. Okay, laminar versus turbulent flow. Let's first define what laminar is. Laminar flow is going to be considered orderly. Adjacent layers do not mix. And the flow is going to follow a general path. And this is generally low velocities or low Reynolds number. Now we haven't really defined Reynolds number as of yet, but we're going to do that today. But let's give you a visual of what's going on. So if we have a path of a flow, you can think of air blowing over a plate or water going over a plate, as we had when we did one of the first demonstrations with viscosity. Viscosity is going to play a part into the Reynolds number. So you have a flow over a plate. It follows an orderly path. So as this is going to go across, we know viscosity is, you can think of as stickiness. So, and again, this is going to give an introduction. So what we're going to have is a boundary layer. Boundary layer is going to continue, but again, you see the orderly path. We'll get more into the boundary layer theory later on. But visually, flow coming in, follows an orderly path, and it just goes very, very, very nicely. You can think of a calm stream on a nice day. The water just follows a very, very nice path. Or when you fill up a sink, the water just goes down the drain. Nothing really overwhelming, mixing, or anything chaotic happens. Turbulent flow. Probably with the name turbulent, you can understand there's going to be some chaotic behavior. Chaotic flow. So therefore it is not laminar. So the things that define laminar, it is going to be not. So this is going to be generally large velocities, Reynolds number. Okay, on your note packets, there's a couple Wikipedia pages that are referenced that have nice visuals of the laminar and turbulent flow. However, now what we would have is flow coming in. If it's going very, 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 very fast, you can have what's going to be going on in here is this mixing. This is going to have different layers of mixing. Going back to where we had adjacent layers do not mix. Well, these layers are adjacent, and you're going to have this mixing going on in here, or it's going to be very chaotic behavior. Ups and downs. Again, a demonstration that we'll go through, you'll be able to see those numbers or see the visualization of the flow. Alright, so we alluded to Reynolds number and viscosity, and also density plays a part in this too. We're going to talk about dimensionless numbers, but that's going to be a little bit later on, the theory of dimensionless, the utilization of dimensionless numbers. But the first one that we're going to introduce is one of the more important ones used in all calculations, Reynolds number. Well, maybe not all calculations, but plays a great role in thermal or with fluid analysis. So Reynolds number. Okay. It's a dimensionless number. That means it's just a number. It's going to have, when you take all the different properties that are going to be in the formula and the units in those properties, you'll see that the result will not have any dimensions in it. So Reynolds number is going to be rho Vx over mu. Mu is the dynamic, rho is the density, V is the velocity, x is going to be a characteristic length. So if we had a flat plate, it could be the length of the plate. If you had a cylinder or a sphere, it could be the diameter of the cylinder. If you're going over the cylinder, or maybe the length. If you're inside a tube, internal flow, again, we're going to get to these different concepts. But it's going to be an important unit of length. So we'll just represent x because it depends on what geometry you have. Now, last class we also went over mu over rho was the kinematic viscosity. So this is also can be written as Vx over nu, where x is some important length, rho is the density, b velocity, and nu is kinematic viscosity, and mu is dynamic viscosity. Okay, so let's go through a calculation. So let's calculate a Reynolds number. So let's give a density of 10, a velocity of 5, we'll do this as kilogram meter cubed, velocity of 5 meters per second. We'll have a unit of length of x equal to 2 meters. And let's come up with a viscosity of 2.5. Okay, let's put some numbers in. Rho Vx over mu. So rho is 10, V is 5, x is 2, and mu is 2.5. Performing that calculation, 10 times 2 times 2, and we'll have a Reynolds number of 40. 40 is going to be our Reynolds number. All right, well, what does that really tell us? Well, there's some parameters or values or ranges of our Reynolds number that are going to tell you if it's laminar or turbulent. So Reynolds number less than 1 times 10 to the third is going to be laminar. If your Reynolds number is in between 10 to the fourth and 10 to the third, we call that flow transition. That means you have a flow. If you're underneath this value, it'll be laminar. Then as it gets faster and faster, and if your Reynolds number is within this range, it starts to get a little bit of turbulence. You might have a period of time where it's turbulent, and then you might have a little period of time where it's not. And then if we have the Reynolds number greater than 10 to the fourth, that's going to be defined as turbulent flow. Laminar flow, transition flow, turbulent flow. Okay, so this particular case that we would have laminar flow. Now again, there's other parameters that are going to affect whether it's laminar or not. That's going to be how rough or smooth the surface is. But general cases, for right now, we'll use these values. And we'll talk about, as the course goes on, different values. But let's go through and let's show that this is going to be a unitless number. Should never assume anything. Basically, you should go through and verify. So density is kilograms per meters cubed. Velocity is meters per second. And distance is a meter. We'll just do over 1. And mu is going to be a Pascal, which is a Newton meter squared times by a second. So we got a fractions divided by fractions. Let's just invert and multiply and do some canceling. So this is a meter squared and a meter and a second here. So I will have a kilogram over a meter times a second on the bottom. Meter squared over meter cubed gives me a meter left over. A kilogram meter over second. And then I take this and invert and multiply. And I have a Newton a meter squared over a Newton times a second. But remembering Newton is going to be a force, which is going to be a kilogram meter per second squared. So let's just substitute that in there. We have a kilogram meter per second squared. Alright. Kilogram here and a kilogram here. A meter squared and a meter squared. Now again, we have another fraction, so we can invert and multiply. So we have a second times a second squared. That's in the bottom, that goes to the top, second squared. They nicely cancel, and therefore we show that this is going to be a unitless or a dimensionless number. Okay, that concludes the discussion on laminar and turbulent and an introduction to dimensionless numbers, Reynolds number. But look on the Wikipedia pages that are referenced and get a good idea of the different visualization. Watch the demonstration next.